You clicked on this video because you want to profile your PyTorch training without killing performance. The reality is that standard profiling tools often stall the GPU entirely while they collect data. If you are running large models or complex pipelines, this hidden synchronization cost can destroy your throughput and make debugging feel like a guessing game. By the end of this explanation, I will show you how to decouple observation from execution so your hardware stays fed even when you are measuring it. Here is the thing about modern GPU training that most tutorials ignore. When you run a standard profiler in PyTorch, you might think you are just gathering statistics quietly in the background. That assumption leads directly into one of the most frustrating failure modes for engineers working with large-scale clusters. The act of capturing kernel timestamps and memory states creates an implicit synchronization point. This forces the GPU to stop what it is doing completely while waiting for the profiler to collect data from every single device involved. Think about your CPU as a conductor leading an orchestra, and the GPUs are the musicians playing in perfect rhythm. In a normal training loop, the CPUs feed batches of data so fast that the GPUs never have time to sit idle. They process tensors continuously at full capacity. However, when you enable traditional offline profiling, something drastic happens. The profiler demands immediate access to the hardware state from every GPU simultaneously. This creates a hard stop in the pipeline where all computation halts until the synchronization barrier is cleared. The result is that your data loading becomes serialized rather than parallelized. While one batch waits for the profiler, the entire cluster sits idle. You might be running on expensive A100 or H800 hardware capable of massive throughput, but you effectively slow it down to a single-threaded pace just because you asked how fast it was going. This feedback loop means that measuring performance becomes slower than actually training without measurement in many scenarios. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This is not just theoretical speculation. There are real-world systems deployed at scale that prove this phenomenon occurs repeatedly. The Eroica system, which has been running across Alibaba Cloud's cluster of 100,000 GPUs for a year and a half, highlights exactly why we need to rethink how we observe training. They found that traditional offline profiling often stalls the GPU due to synchronization overhead, negating any performance gains from modern hardware pipelines. Eroica achieved a 97.5% success rate in diagnosing complex hardware-software interactions, specifically because it avoided these latency spikes associated with generating full profiling traces. This massive deployment validates the core premise that asynchronous or CPU-side observation is necessary if you want to keep GPUs fed during training. Without this approach, your diagnostics become part of the problem rather than a solution. Most existing frameworks like XPU Timer and Reveal focus on anomaly detection or raw hardware telemetry instead of specific PyTorch profiling techniques. They tell you when something broke, but do not help you understand why your data pipeline is serializing during active training. The Apex paper addresses CPU-GPU parallelism, yet it focuses primarily on inference workloads rather than the dynamic nature of distributed training loops. This leaves a significant gap in direct benchmarks comparing asynchronous profiling overhead against standard PyTorch tools like torch.profiler for production environments. You must distinguish between coarse online monitoring and full offline profiling to solve this effectively. Coarse monitoring lacks the granularity needed to debug complex hardware-software interactions, while full offline profiling is too resource-intensive for live production use. The solution lies in a hybrid approach that samples asynchronously to maintain GPU utilization without sacrificing insight. Engineers often assume measuring performance is free, but capturing kernel timestamps creates overhead that stalls the compute path unless handled differently. PyTorch Profiler version 1.9 and later introduced improvements with its distributed training view, which identifies stragglers and NCCL imbalances without blocking the main training loop. This allows engineers to diagnose bottlenecks in real time while keeping the critical execution path open. However, even these newer tools require careful configuration because they still rely on sampling strategies that can introduce latency if not tuned correctly for your specific workload scale. The primary failure mode remains the assumption that observation does not impact performance. In reality, every time you capture a timestamp or read memory state from a GPU, you interrupt its flow. This requires shifting to non-intrusive CPU resident instrumentation, where profiling data is buffered locally on the host processor rather than forcing immediate synchronization with the accelerator cards. Consider how Eroica handles this by using asynchronous sampling and CPU-side buffering to decouple overhead from the critical path. The system allows fine-grained PyTorch profiling with minimal impact on production performance because it does not wait for every kernel to finish before recording data. Instead, it collects samples continuously in parallel while training proceeds uninterrupted. This is why they could achieve such high diagnostic success rates across a massive cluster without introducing noticeable latency spikes that would disrupt active workloads. For you as an engineer learning production-grade development, the takeaway is clear. You need to stop treating profiling like a snapshot tool and start thinking of it as a continuous monitoring system. If your goal is to maintain maximum throughput while diagnosing issues, you must adopt methods that observe without stopping execution. This means prioritizing asynchronous collection mechanisms over synchronous blocking calls whenever possible. The gap in current benchmarks suggests that while asynchronous profiling remains a specialized solution primarily validated in massive cluster environments like Alibaba's, the principles apply universally to any training loop where latency matters. Even if you are not running 10,000 GPUs, the mechanics of Cuda synchronization and data loading serialization remain identical regardless of scale. Understanding this distinction allows you to choose the right tool for your specific iteration speed needs rather than defaulting to a standard profiler that might be slowing down your development cycle more than it helps. By shifting your mindset from measuring performance as an afterthought to integrating non-intrusive observation into your training pipeline, you ensure that every second of compute time contributes directly to model convergence. This approach prevents the common pitfall where debugging becomes a bottleneck in itself, allowing you to iterate faster and trust the metrics you collect without fearing they are distorting reality. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.